Hello everyone, and welcome to today's video lecture, which is on the exponential generating function for Bernoulli numbers and for Bernoulli polynomials. And our goal for today's lecture is very straightforward. We're going to derive the exponential generating function for Bernoulli numbers, and then we're going to do the same thing. We're going to derive the exponential generating function for the related concept of Bernoulli polynomials. But before we do that, I'm going to just ask you to recall what exactly the Bernoulli numbers are. Well, the Bernoulli numbers, which we discussed in my lecture on the Euler-Maclaurin summation formula, are a very special sequence of rational numbers that occur all over mathematics. They occur, of course, in the Euler-Maclaurin summation formula, but they also show up in other contexts, for example, in the evaluation of the zeta function. So I'll just list the first few Bernoulli numbers so that we have a feel for what we're working with in this lecture. And I'll follow convention by writing the first Bernoulli number as b sub 0. So b sub 0, that equals 1. The next Bernoulli number, b sub 1, that equals negative 1/2. b sub 2 equals 1/6. b sub 3 equals 0. b sub 4 equals negative 1/30. b sub 5 equals 0. b sub 6 equals 1/42. b sub 7 equals 0 again. You might start seeing a pattern now. b sub 8 equals negative 1/30 again. b sub 9 equals 0. And b sub 10 equals 5/66. And so on. Now, on visual inspection, it might be very difficult to deduce a pattern that determines how these Bernoulli numbers are produced. Yes, we might note that the odd subscripted Bernoulli numbers greater than b sub 1, so in other words, b sub 3, b sub 5, b sub 7, and so on, yes, those all equal 0. We also note that Bernoulli numbers are rational, and we also note that the even subscripted Bernoulli numbers alternate signs. But there's in fact no explicit formula for determining the Bernoulli numbers. They can, however, be determined by this recursive formula, which I derived in the last video on the Euler-Maclaurin summation formula. And the recursive formula says that the nth Bernoulli number, b sub n, equals the negative of the sum, indexed from k equals 0 to n minus 1, of the binomial coefficient n choose k times b sub k over n minus k plus 1. Now it turns out there are other recursive formulae for the Bernoulli numbers, but this is one of the most well-known and well-studied ones. Now, admittedly, this formula takes some unpacking, but I've already done that in my previous video on the Euler-Maclaurin summation formula. So if you're at all puzzled by that recursive formula for the Bernoulli numbers, I would just encourage you to go take a look at that video. Instead, what I'm going to do is use that formula as a jumping off point for the material that follows. Because from this recursive formula, which again I derived in the previous video, we'll obtain the following identity, which we'll need. It's just basically a rewriting of the recursive formula. We'll say that the sum from k equals 0 to n, indexed from k equals 0 to n, of the binomial coefficient n plus 1 choose k times b sub k equals 0. So to see why this identity is true, let's derive it for the case of b sub 3. So we know from our recursive definition of the Bernoulli numbers that b sub 3 is going to equal the negative of the sum indexed from k equals 0 to 2. Remember, we're letting n equal 3, and then the sum goes up to n minus 1, so there's a 2 there, of 3 choose k times b sub k over 3 minus k plus 1. So let's unpack this sum then. B sub 3 would equal the negative of Now I'm going to add up our terms. 3 choose 0 times b sub 0 over 3 minus 0 plus 1 plus 3 choose 1 times b sub 1 over 3 minus 1 plus 1 plus 3 choose 2 times b sub 2 over 3 minus 2 plus 1. So I hope you can see how this formula is recursive. We can only determine b sub 3 after we know b sub 0, b sub 1, and b sub 2. So now I'm just going to clean up these denominators and shift things over a little. And then I'm going to do something really clever. I'm going to multiply both sides of this equation by the binomial coefficient 4 choose 3. Well, let's work out what those binomial coefficients actually mean. 4 choose 3 is 4 factorial over 1 factorial times 3 factorial. This is multiplying b sub 3. And it equals the negative of the sum of 3 choose 0, which is 3 factorial over 3 factorial times 0 factorial, times b sub 0 over 4, plus 3 factorial over 2 factorial times 1 factorial times b sub 1 over 3, plus 3 factorial over 1 factorial times 2 factorial times b sub 2 over 2. And this is all being multiplied by 4 choose 3, which is 4 factorial over 1 factorial times 3 factorial. So when we do that, something really cool happens on the right-hand side of this equation. The 3 factorials in the denominators of all those terms cancel, and then I can distribute the 4 factorial to all of those terms. Next thing to notice is that the denominator of those terms can be simplified. The 4 can be pulled into the factorial term, so 4 times 3 factorial is 4 factorial, so that's 4 factorial times 0 factorial. The next term would become 3 factorial times 1 factorial, and the last term would become 2 factorial times 2 factorial. And having done those simplifications, we can rewrite everything again in terms of binomial coefficients. So we'll have 4 choose 3 times b sub 3 equals the negative of the sum of 4 choose 0 times b sub 0 plus 4 choose 1 times b sub 1 plus 4 choose 2 times b sub 2. And now I'll just distribute the negative sign and then move everything over to the left-hand side. So we'll have 4 choose 0 times b sub 0 plus 4 choose 1 times b sub 1 plus 4 choose 2 times b sub 2 plus 4 choose 3 times b sub 3 equals 0, which is exactly what our identity in that box in the upper right-hand side of the screen indicates in more general form. So I'm not going to do a general proof of this identity in this video, but for those of you that are curious about it, I hope the procedure that I just outlined above is very clear for what we would do in general. We would start with b sub k, using our recursive definition of the Bernoulli numbers, multiply both sides of the equation by the binomial coefficient k plus 1, choose k, simplify and rearrange terms, and we would get the identity that we want. So why am I going to all the trouble of deriving that identity? Well, you'll see now that we actually need it for the main subject of today's video. And we're going to derive another way of producing Bernoulli numbers, namely through the Maclaurin series of a very special function. We're going to show that the Bernoulli numbers can also be represented as the coefficients in this Maclaurin series. And our function is going to be the function f of x equals x over e to the x minus 1. And because this function has that special property, it's given a special name. It is called the exponential generating function for the Bernoulli numbers. So how do we derive this amazing result? Well, to do so, we first need to consider, in a more general context, what happens when we multiply two Maclaurin series together. Specifically, when we multiply the Maclaurin series of the function e to the x by the general Maclaurin series for some unspecified function f of x. Well, let's write out these series to see what they look like. the Maclaurin series for e to the x, that just equals x to the 0 over 0 factorial, plus x to the 1 over 1 factorial, plus x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the 4th over 4 factorial, and so on, plus dot, dot, dot. Our Maclaurin series for a general function, an unspecified function f of x, well, we have to write it in terms of f of x and all of its derivatives. It equals f of 0 times x to the 0 over 0 factorial, plus f prime of 0 times x to the 1 over 1 factorial, plus f double prime of 0 times x squared over 2 factorial, plus f triple prime of 0 times x cubed over 3 factorial, plus the fourth derivative of f evaluated at x equals 0 times x to the 4th over 4 factorial, plus dot, 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 and so on. So these are the Maclaurin series for those two functions, for e to the x and for f of x. And so the natural question emerges, since these are both infinite series, is how should we multiply these two series together? And the very great mathematician Cauchy showed us all how to do this. And so the method of multiplying these infinite series is named after him, and it's termed the Cauchy product. And here's how it works. When we multiply these two infinite series together, what we're really doing is producing an infinite two-dimensional array of numbers. And we can make a chart to see how each term in the Maclaurin series for e to the x multiplies each term in the Maclaurin series for f of x. So I'm going to write the Maclaurin series for e to the x up top here. I've got x to the 0 over 0 factorial, plus x to the 1 over 1 factorial, plus x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the 4th over 4 factorial, plus dot, 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 and so on. That equals my Maclaurin series for e to the x. And every term in that function is going to multiply all the terms in this column, where I'm going to write the terms for the Maclaurin series of f of x. So I have my first term f of 0 times x to the 0 over 0 factorial, plus f prime of 0 times x to the first power over 1 factorial, plus f double prime of 0 times x squared all over 2 factorial, plus f triple prime of 0 times x cubed over 3 factorial, plus the fourth derivative of f evaluated at x equals 0 times x to the 4th over 4 factorial, plus dot, dot, dot. So I'm only showing the first 4 terms of each of these functions. This two-dimensional array of terms, of course, is infinite, but at least we can start seeing what's going on in this product when we multiply these two things together. So when we do that, the upper leftmost term would be f of 0 times x to the 0 over 0 factorial times x to the 0 over 0 factorial. The term just below that would be f prime of 0 times x to the first power, again multiplying that top term x to the 0 all over 1 factorial times 0 factorial. For those of you that are familiar with linear algebra, this is a lot like filling out the entries in a matrix when we multiply a column vector by a row vector. Anyway, our next entry would be f double prime of 0 times x squared times x to the 0 all over 2 factorial times 0 factorial. And moving down, the next entry would be f triple prime of 0 times x cubed times x to the 0 all over 3 factorial times 0 factorial. The term after that would be the fourth derivative of f evaluated at x equals 0 times x to the 4th times x to the 0 all over 4 factorial times 0 factorial, and so on. Now remember, all of the terms in this two-dimensional array are being added together. I'm just not writing in the plus signs because it would be too messy. And I did the first column of this array for a reason, which is that first term of e to the x, x to the 0 over 0 factorial, that just equals 1. So if I were to sum up all the terms in this first column of the array, those terms would just equal f of x. And now, to sum all the other terms in this array, I'm going to employ a very clever trick used by Cauchy. We're going to sum along the diagonals. So you'll see what I mean in a moment. So let's get our first term here. That would be f of 0 times x to the 0 times x to the first power all over 0 factorial times 1 factorial. And I'm going to put a little box around that term. Okay, this is going to be the first diagonal, and it contains only one element, this term. Okay, moving ahead to the next term that we're going to sum, let's multiply f of 0 times x to the 0 times x squared all over 0 factorial times 2 factorial. And then moving down to the left along the diagonal, I'm going to group that together with this product here, f prime of 0 times x to the first times x to the first all over 1 factorial times 1 factorial. So I'll put a little box around those two terms together, and then I'll move on to the next diagonal. So at the top right of that diagonal, we'll have f of 0 times x to the 0 times x to the third power all over 0 factorial times 3 factorial. Next, we'll have f prime of 0 times x to the first times x squared all over 1 factorial times 2 factorial. And then moving down to the left along the diagonal, the last term in this grouping will be f double prime of 0 times x squared times x to the first over 2 factorial times 1 factorial. So I'll put another box around these terms together as a group. And I hope some of you are starting to see why this is such a great way to sum this product of terms, because we're going to be adding up these terms in groups along the diagonals. And when we do that, we'll see an amazing pattern. Well, let's just do one more diagonal here. We'll do f triple prime of 0 times x cubed times x to the first all over 3 factorial times 1 factorial. And then moving up and to the right, we'll have f double prime of 0 times x squared all over 2 factorial times 2 factorial plus f prime of 0 times x to the first times x cubed all over 1 factorial times 3 factorial. And then the fourth and final term along this diagonal will be f of 0 times x to the 0 times x to the fourth all over 0 factorial times 4 factorial. So I'll just put a box around those terms in that grouping along the diagonal there. But again, these terms are all being added together, and this is an infinite array. Now, obviously, I can't write out every single term in this Cauchy product, but I hope I've done enough to illustrate how summing them up will work. And we'll see that in just a moment here. So I've taken all those groupings along the diagonals, and I've written them out. So we have f of x times e to the x equals this infinite sum. And the very first thing to do to simplify it is to just combine exponents in all of the numerators of these terms. So I've done that here. Well, what else can we do to simplify this sum on the right-hand side? Well, you may notice if you look at the terms in parenthesis, they all contain an x raised to some exponent. The first parenthetical grouping contains x squared terms. So I can pull that out. I can factor that out from that grouping. The next three terms in parenthesis all contain an x cubed, so I can factor out an x cubed there. And I can factor out an x to the fourth from the next parenthetical grouping of 4 terms. And you can imagine if I had summed up along all the diagonals, I would always be able to factor out an x to some exponent. And that exponent actually equals the number of terms in the parenthesis. Well, what else can we do to simplify this expression? Well, if you look at all the terms in parenthesis and really look at their denominators, you'll see that all of those denominators have 2 different factorial terms being multiplied together. Well, that should immediately remind us of the binomial coefficient. And so we can do something really clever here. We can multiply each term by what a math teacher of mine used to call a creative form of 1. So I'll do that here after the f of x term. The term right after that, I'm going to multiply it by 1 factorial over 1 factorial. And then the first grouping of terms in parenthesis, I'm going to multiply that one by 2 factorial over 2 factorial. The one after that, I'm going to multiply it by 3 factorial over 3 factorial. And the last parenthetical grouping I've written down here, I'm going to multiply that one by 4 factorial over 4 factorial. And when we do this, something really awesome happens. So to illustrate, I'm going to just focus on that last parenthetical grouping of 4 terms. I'm going to distribute that 4 factorial to each of those terms in parenthesis. And when we do that, we get the binomial coefficients. So the first term will then become 4 choose 0 times f of 0. The next term will be 4 choose 1 times f prime of 0. The term after that will be 4 choose 2 times f double prime of 0. And the last term in parenthesis will be 4 choose 3 times f triple prime of 0. And then I'll just move that 4 factorial in the denominator over to the right-hand side, so this parenthetical grouping will be times x to the fourth over 4 factorial. Well, the exact same thing happens for our parenthetical groupings of the other terms. For the terms multiplying x to the third, we end up with 3 choose 0 times f of 0 plus 3 choose 1 times f prime of 0 plus 3 choose 2 times f double prime of 0, all times x to the third over 3 factorial. For our 2 terms in parenthesis, we get 2 choose 0 times f of 0 plus 2 choose 1 times f prime of 0 times x squared over 2 factorial. And then that single term there is 1 choose 0 times f of 0 times x to the first over 1 factorial. So this is looking really good. And now, knowing what we already know about the Bernoulli numbers, we might ask ourselves, under what conditions, under what circumstances, would all of these combined terms in parentheses add up to 0? And the answer is, well, that would happen if f of 0 was equal to the first Bernoulli number, which we actually designate b sub 0, and if f prime of 0 were equal to b sub 1, and if f double prime of 0 were equal to b sub 2, and if f triple prime of 0 were equal to b sub 3, and I haven't shown it here, but if, of course, f quadruple prime of 0 were equal to b sub 4, and f5 of 0 were equal to b sub 5, remember that this is an infinite sum, and because of the way that I've summed these terms along the diagonals, all of the terms are going to be grouped into parentheses, then I claim that if in general fn of 0 equals b sub n, then all of these terms in parentheses must sum to 0 because of the identity concerning Bernoulli numbers that I described at the beginning of this video. Well, if that is the case, then all we have left of this equation is f of x times e to the x equals f of x plus 1 choose 0 just equals 1 times x to the first over 1 factorial. So we just get f of x times e to the x equals f of x plus x. Again, provided, and this is a very big provided, provided that fn of 0 equals b sub n. Now notice that we don't even know yet what f of x should equal, but we're about to figure it out, because we can solve this equation for f of x. So I'll do that. I'm going to subtract f of x from both sides here. So I'll have f of x times e to the x minus f of x equals x. Then I'm going to factor out f of x from the left-hand side of the equation. So we'll have f of x times, open parenthesis, e to the x minus 1 equals x. And now I'll divide both sides of the equation by e to the x minus 1 to find that f of x must equal x over e to the x minus 1. So that's a very important result for us, and I'm going to put a box around it. So we have f of x equals x over e to the x minus 1, and this is the exponential generating function for the Bernoulli numbers. And we call it the exponential generating function because this function generates the Bernoulli numbers. It gives us another way of deriving them without using recursive formulae, because it turns out that the Maclaurin series for the function f of x equals x over e to the x minus 1 has the Bernoulli numbers for all of its coefficients. Now, why is that? Well, remember that the general form of a Maclaurin series is f of x is equal to f of 0 times x to the 0 over 0 factorial plus f prime of 0 times x to the first over 1 factorial plus f double prime of 0 times x squared over 2 factorial plus f triple prime of 0 times x cubed over 3 factorial plus f quadruple prime of 0 times x to the fourth over 4 factorial plus f5 of 0 times x to the fifth over 5 factorial plus dot dot dot. But here we know what f of 0 and f prime of 0 and f double prime of 0 must equal. F of 0 must equal b sub 0. F prime of 0 must equal b sub 1. F double prime of 0 must equal b sub 2, and so on. In fact, we can write if f of x equals x over e to the x minus 1, then this function can be written as the Maclaurin series, which is the sum, indexed from k equals 0 to infinity, of b sub k times x to the k over k factorial. Well, with a result this dramatic, it's probably a good idea to do a little reality check. So let's find f of 0. Well, f of 0 would be 0 over e to the 0 minus 1. So that's 0 over 1 minus 1, or just 0 over 0. Well, 0 over 0 is an indeterminate form, but it can be evaluated using L'Hopital's rule. So to do that, we take the limit as x approaches 0 of the function x over e to the x minus 1, and then we differentiate both the numerator and the denominator. And so this will equal the limit as x approaches 0 of 1 over e to the x, and that equals 1 over e to the 0, which equals 1 over 1, which just equals 1, and that happens to equal b sub 0, the first Bernoulli number. Now let's check and see whether f prime of 0 equals b sub 1. Well, to do that, we have to find f prime of x. Now to do that, I have to apply the quotient rule since this function is a quotient. So we have f prime of x equals the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. So this will equal e to the x minus 1 times 1 minus x times e to the x all over quantity e to the x minus 1 squared. And that equals e to the x minus 1 minus x times e to the x all over e to the x minus 1 times e to the x minus 1. And now that equals, simplifying the denominator, e to the x minus x times e to the x minus 1 all over e to the 2x minus 2 times e to the x plus 1. Now when we plug in 0 for x, we get that f prime of 0 equals e to the 0 minus 0 times e to the 0 minus 1 all over e to the 2 times 0 minus 2 times e to the 0 plus 1. Well, e to the 0 just equals 1, and then minus 0 times e to the 0, that just equals 0, and then we have a minus 1. So overall in the numerator we have a 1 minus 1, which equals 0. Then in the denominator, e to the 2 times 0 equals 1, and then we have minus 2 times e to the 0, so minus 1 plus 1. So we have 1 minus 2 times 1 plus 1, so we also have a 0 in the denominator. So we have a 0 over 0 expression, and we need to use L'Hopital's rule to evaluate f prime of 0, just as we had to use it to evaluate f of 0. So then we have the limit as x approaches 0 of f prime of x equals, now applying L'Hopital's rule, we differentiate the numerator and the denominator. The limit as x approaches 0 of, here's the derivative of the numerator, e to the x minus x times e to the x. This is the product rule. So then plus 1 times e to the x, okay, close brackets, all over 2 times e to the 2x minus 2 times e to the x. So I can simplify the numerator there a little bit to get that this equals negative x times e to the x over 2 times e to the 2x minus 2 times e to the x. And now, when I plug in 0 for x, I still get a 0 over 0 expression. So we have to apply L'Hopital's rule again. So this will equal the limit as x approaches 0. Differentiating the numerator, we get negative, open parenthesis, x times e to the x plus 1 times e to the x, close parenthesis, all over 4 times e to the 2x minus 2 times e to the x, which then equals, plugging in 0 for x, negative 0 times e to the 0 plus 1 times e to the 0 over 4 times e to the 2 times 0 minus 2 times e to the 0. Now 0 times e to the 0 just equals 0. And then we have a 1 times e to the 0. So with that negative sign in front there, we have that this equals negative 1 over 4 minus 2, or just negative 1/2, which equals b sub 1. So the moral of the story is this really works. So this exponential generating function f of x, which equals x over e to the x minus 1, gives us another way to define the Bernoulli numbers, instead of just using a recursive definition. But Euler went a step further, and he did that by asking the question, what happens when we multiply the Maclaurin series for x over e to the x minus 1 by another copy of e to the x, but I'll use a different variable here. I'll call it by e to the y. Well, remember that x over e to the x minus 1 equals, if we write it out as its Maclaurin series, b sub 0 times x to the 0 over 0 factorial plus b sub 1 times x to the first power all over 1 factorial plus b sub 2 times x squared over 2 factorial plus b sub 3 times x cubed over 3 factorial plus dot dot dot. And the Maclaurin series for e to the y would equal y to the 0 over 0 factorial plus y to the first power over 1 factorial plus y squared over 2 factorial plus y cubed over 3 factorial plus dot dot dot. And once again, we'll use the Cauchy product to see what would happen if we multiply these two series together. So I've written out our two series here again to form a two-dimensional array. I've written the Maclaurin expansion for x over e to the x minus 1 in the top row there, and I've written e to the y in the leftmost column there. And our first term, when we multiply these two series together, would be b sub 0 times x to the 0 times y to the 0 all over 0 factorial times 0 factorial. So we can put a box around that term and go to the next diagonal. So moving down, we would have b sub 0 times x to the 0 times y to the first all over 0 factorial times 1 factorial. And then moving up and to the right, we would have b sub 1 times x to the first times y to the 0 all over 1 factorial times 0 factorial. So we can put another box around that diagonal, and then the next entry would be in the diagonal after that, b sub 0 times x to the 0 times y squared all over 0 factorial times 2 factorial. Then moving up and to the right, we would have b sub 1 times x to the first times y to the first over 1 factorial times 1 factorial. Then moving up along the diagonal again, we would have b sub 2 times x squared times y to the 0 all over 2 factorial times 0 factorial. I'll put a box around that diagonal, and then I'll just do one more diagonal. Starting on the bottom left, we have b sub 0 times x to the 0 times y cubed all over 0 factorial times 3 factorial. Then moving up and to the right, we have b sub 1 times x to the first times y squared all over 1 factorial times 2 factorial. Moving up and to the right again, we have b sub 2 times x squared times y to the first all over 2 factorial times 1 factorial. And then finally, we have b sub 3 times x cubed times y to the 0 all over 3 factorial times 0 factorial. So I'll put another box around that diagonal. And remember, all of these terms are being added together. It is an infinite sum. But I can't keep doing this all day long, so hopefully by now the pattern is clear. I'm just going to write plus dot 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 plus dot dot dot. So I've taken all these terms that are grouped on the diagonal and laid them out in rows. And now the next clever thing Euler did was to make a variable substitution for y. He said, let's let y equal x times some variable which we'll call t. So now what I'm going to do is substitute in x times t for all the y's in this expression. So that first term there will become b sub 0 times x to the 0 times quantity x times t to the 0 over 0 factorial times 0 factorial. The first term in parentheses right below it will be b sub 0 times x to the 0 times quantity x times t to the 1 all over 0 factorial times 1 factorial, and so on for all the others. The next step would be to distribute the exponent in all of those xt terms. And then we can just combine our exponents in x, so x to the 0 times x to the 0 is just x to the 0, x to the 1 times x to the 0 is just x to the 1, and so on. Next, we can just factor out these x terms from these expressions. Then we can employ the same trick that we used before. We can multiply these parenthetical expressions by a creative form of 1. So I'll multiply the top one by 1 factorial over 1 factorial, the next one below that by 2 factorial over 2 factorial, and the bottom expression by 3 factorial over 3 factorial. So for that bottom expression, I'll distribute that 3 factorial into the numerator of all of those terms. So when I do that, we know what happens. That just gives us the binomial coefficients. So I've written them there in the bottom expression, and when we distribute the 2 factorial into the numerator of those terms in the parenthetical expression above it, the exact same thing happens. We get the binomial coefficients there as well. And the same thing happens with the top expression. Well, what's so great about this? Well, by making these simplifications, we now have a new Maclaurin series where the coefficients in this Maclaurin series are just these expressions that are in the parentheses. And these expressions in the parentheses are quite special. They are polynomials in T that in a certain sense marry together the binomial coefficients with the Bernoulli numbers. And these coefficients are given a special name. They're known as the Bernoulli polynomials. And this function, x over e to the x minus 1 times e to the x times t, is called the exponential generating function for the Bernoulli polynomials. So I've taken those expressions and just listed them here, and I suppose it needs to be said that the first Bernoulli polynomial, which we'll call b0 of t, is very simple. It just equals b sub 0, which equals 1. And then the next Bernoulli polynomial we'll call capital B sub 1 of t, and the one after that would be b sub 2 of t, and then b sub 3 of t, and so on. So let's try to actually unpack what some of these expressions mean. Looking at b sub 1 of t, 1 choose 1 and 1 choose 0 just both equal 1. So we get b sub 1 of t equals b sub 0 equals 1, so 1 times t to the first, plus 1 times b sub 1, which is negative a half, so minus 1/2 times t to the 0. So this expression just equals t minus 1/2. Now looking at b sub 2 of t, the coefficient 2 choose 2 just equals 1, 2 choose 1 equals 2, and 2 choose 0 equals 1. So we get that this equals 1 times b sub 0, which is 1, times t squared, minus 2 times a half times t to the first, plus 1 times b sub 2, which is 1/6, times t to the 0. So this expression equals t squared minus t plus 1/6. Now looking at b sub 3 of t, the coefficient 3 choose 3 equals 1, 3 choose 2 equals 3, 3 choose 1 equals 3, and 3 choose 0 equals 1. So we get b sub 3 of t equals b sub 0 times t cubed, so 1 times t cubed, minus 3 times a half times t squared, plus 3 times 1/6 times t to the first, plus 1 times 0 times t to the 0. And that equals t cubed minus 3 halves t squared plus 1/2 times t to the first plus 0. So I'll just put a box around those results, and we find that in general, the kth Bernoulli polynomial, so b sub k of t, equals the sum indexed from k equals 0 to n of the binomial coefficient n, choose n minus k, times b sub k times t to the n minus k. Now, if you look at the first few of these Bernoulli polynomials, you'll see something which is actually a general pattern, which is that if we set t equal to 0, we just get back for the nth Bernoulli polynomial the constant term, which is the nth Bernoulli number. Also, if we set t equal to 0 in our exponential generating function for the Bernoulli polynomials, which again was x times e to the x times t, all over e to the x minus 1, by setting t equal to 0, that e to the xt term becomes e to the 0, which just equals 1. So once again, we'd get back our exponential generating function for the Bernoulli numbers. So in this sense, the Bernoulli polynomials are a generalization of the Bernoulli numbers. And these Bernoulli polynomials have all kinds of interesting and really amazing properties, but that's a topic for another day. And I'll also just add that they show up in the remainder term for the Euler-Maclaurin summation formula. Remember that I've given that formula so far without the remainder term, but when you derive that formula with the remainder term, the Bernoulli polynomials show up there. But I think we covered enough ground already, so I'll stop here. Thanks so much for watching this video, and if you enjoyed it, please like or subscribe to my YouTube channel. Thanks again.